In this final video, we will talk about how to evaluate different Lewis structures, and if we think one possible Lewis structure contributes more to the actual structure than other possible structures. So, as you can see in your notes, not all resonance structures are considered equal. Sometimes one resonance structure contributes more to the real structure of the molecule. And we're going to determine which ones we think contribute more by something called formal charge. This is a new vocabulary word, formal charge or formal charges. We are going to assign formal charges to each atom in the structure. This is how we're going to do it. For each atom, we're going to count the electrons in lone pairs, and we're going to count half. This means count half of the electrons that atom shares with other atoms. So let's see how we're doing that down here. So we're going to count the electrons in lone pairs around oxygen. We're just going to look at oxygen right now. Oxygen has 4 lone pairs. So I'm going to write that here. 4 LPs, 4 LP electrons. 2 lone pairs are 4 lone pair electrons. And this other thing we're going to do up here, we're going to count half of the electrons it shares with other atoms. Oxygen is sharing half. These are 2 bonds between oxygen and carbon. 2 bonds would be 4 electrons. Oxygen shares that, so we're going to count half of those electrons. So if these 2 bonds have 4 electrons, half of them would be, half of 4 is 2. So we have 2 bonded electrons that we're going to assign to oxygen. So what we just counted up was this. I'm circling it in green. Those are the electrons assigned to the atom. Now the number of valence electrons that oxygen has possible for it are 6. We know that. It's in the periodic table. Oxygen's valence structure is S2P4, giving it 6 possible valence electrons. So these are the 6 possible valence electrons it has. To find the formal charge, we subtract what we just calculated, the electrons assigned to that atom. I'm going to call these the electrons. I did this in the wrong color. Hold on. This is what I calculate, what I circled in green down there. These are the electrons assigned to the atom. And what I circled in red were the valence electrons. And the difference is Fc, or formal charge. Fc is formal charge. So for oxygen here, the formal charge on the oxygen atom is 0. If we did the same thing for carbon, carbon has 4 possible valence electrons. If we look here, it's sharing, we're going to count half of these electrons it shares with oxygen, so that's 2, and half of these electrons it shares with oxygen over here, so that's another 2, so it has 4 that it shares, so the difference between its 4 valence and the 4 that it shares is 0. Here, we have another oxygen. It looks exactly like this one. It has 6 possible valence, and it has 6 electrons assigned to it, so its formal charge is 0. Let's look over here at this possible structure. This is also a possible Lewis structure for carbon dioxide, because each atom has 8 electrons, an octet, if you look at it carefully. Let's see what the formal charge is for each atom here. Again, the top line isn't going to change because the possible valence electrons for oxygen, carbon, and oxygen are the same, 6 and 4. But in this oxygen that I'm circling now with my pointer, it has 7 electrons assigned to it. It has 6 lone pair electrons, and then another one from the sharing of this pair. That makes a total of 7. So the formal charge on this oxygen is -1. For the carbon is sharing 1 electron here. Well, it has 1 that's assigned to it here and 3 here. We're just taking half of the pairs. So its electrons assigned to it are 4, so its formal charge is still 0. Over here, the oxygen has 2 lone pair electrons, and then half of this triple bond, so it's another 3. So a total of 5 electrons that are assigned to it in this configuration. The difference 6 minus 5 is +1. So notice the overall charge on this molecule would still be 0 because you have 0 and then you have -1 and +1. The -1 and +1 cancel. And the informal charge is just a construct. It's a way of evaluating things. But we're going to say that this structure is more likely because its formal charges are all 0. Your more likely structure is going to be the one with its formal charges that are closest to 0. So this is more likely to be the real Lewis structure. This is less likely. You could also tell this experimentally. This bond would be much shorter than this one, so that would be another way to decide if this was the correct one. So we know from experimental data and also the formal charges that this is the more correct Lewis structure. So let's figure out the formal charges for each atom in this structure. And first we have to flesh it out. We have sulfur, carbon, and nitrogen. Sulfur has 6 valence electrons. Carbon has 4. Nitrogen has 5. So 9 plus 6 is 15. Plus we have an extra electron here because this has a negative charge. So a total of 16 electrons. There are 1, 2, 3, 4, 5, 6, 7, 8 that are distributed here. I'm going to rewrite this so we have it like, that's taking up my room. I'm going to do it over here. Carbon already has 8, so 8 electrons have been distributed, so I'm going to take away 8. That leaves 8. So if I put 2 lone pairs there and 2 lone pairs there, that's 1, 2, 3, 4, that's another 8. That gets me to 0, and I have everything looks like it has an octet. So this is a potential structure. This is the Lewis structure for this. So now we're going to evaluate the formal charge on the sulfur, carbon, and nitrogen. So sulfur has a possible 6 valence electrons. Carbon has a possible 4. Nitrogen has a possible 5. Something's going to have an extra electron because we added 1 here. So these are the valence. We're going to take away electrons that are assigned to them, and our formal charge, our Fc, will be the difference. So let's look at sulfur. Sulfur here has 1, 2, 3, 4 electrons plus half of this double bond, which is another 2. So sulfur has 6 electrons assigned to it. 6 minus 6 is 0. Let's look at carbon. Carbon has half of this double bond and half of this double bond. That's 2 and 2, so that's 4 electrons. 4 minus 4 is 0. Let's look at nitrogen. Nitrogen has, half of this double bond, that's 2 electrons, plus 1, 2, 3, 4, plus 4 electrons from lone pair, so that's 6. So 5 minus 6 is minus 1, so the formal charge on the nitrogen is minus 1. Which makes sense. One of these atoms had to have a minus 1 charge because the overall ion has a minus 1 charge. There's no resonance structure here. This is the Lewis structure, and that's what it is. So as I said earlier, the best Lewis structure is the one with the fewest charges, which means the most zeros. And also the best Lewis structure is the one that ends up putting the negative charge on the most electronegative atom. So if we were to evaluate this down here, let's write in our potential. This has 5 valence electrons, this has 4, this has 6. That's going to be the same for each one. Now let's see how many electrons are assigned in each one. In this case, this one has 6 lone pair electrons plus 1, so that would be 7. So 5 minus 7 is minus 2. I'm going to scribble that in here. The carbon has 1 plus half of this bond plus half of this bond, so 4 electrons assigned to it. 4 minus 4 is 0. The oxygen in this structure has half of this, so that's 3 plus 2, so that's 5 electrons. So this is plus 1. Over here, this nitrogen has 4 lone pairs plus half of this bond, so that's 6 electrons, giving it a -1 formal charge. The carbon still has 4, nothing changed there. The oxygen has 1, 2, 3, 4 lone pairs. That's 4 electrons plus half of this. That's 6. So the oxygen is 0. Let's look at this one. It's already circled, so you're guessing it might be right. The nitrogen has half of this triple bond, so that's 3 plus 2. It has 5 electrons assigned to it, so its formal charge is 0. The carbon has 4 electrons assigned to it, so its formal charge is 0. The oxygen has 1, 2, 3, 4, 5, 6 lone pair electrons plus half of this bond, so that's 7 electrons assigned to it, so the oxygen's formal charge is -1. So in this case, both this structure and this structure have the fewest charges. They both have 2 zeros. But the difference between this one and this one is that this one puts the negative charge on the more electronegative atom, which is oxygen. So that's why this one is the most likely or the best possible structure for this atom, because the negative charge is most likely to be on the most electronegative atom. I'm going to stop this video here, and we will go through the rest of the notes in class.